Big news, space fans! The James Webb Space Telescope has done something groundbreaking. It captured its first ever direct image of an exoplanet. That's right, a real planet beyond our solar system. This is the kind of thing that makes astronomers giddy, and it should make you excited too. But before you imagine a stunning high-definition cosmic masterpiece, let's talk about what the image actually looks like. Why can't James Webb Space Telescope give us a clear picture? The simple answer: size matters. If we wanted to capture an Earth-like planet with the kind of detail that lets us see oceans, landmasses, and swirling clouds, we'd need a telescope lens that's about 90 kilometers in diameter. That's 55 miles the distance from New York City to Bridgeport, Connecticut. And that's just for a 1-pixel image. Now let's say we want something clearer, like a 10-pixel image, which is still basically useless for seeing any details. That would require a 900-kilometer wide telescope, which is roughly the size of Germany. So unless we suddenly figure out how to launch entire countries into space, we need a different plan. Enter the solar gravitational lens. Since we can't build mega-sized space telescopes, scientists have come up with an ingenious solution, using our own sun as a giant magnifying glass. This concept, known as the solar gravitational lens, takes advantage of Einstein's theory of general relativity, which states that massive objects like stars can bend light around them. If we position a telescope in just the right spot, we can use the sun's gravitational pull to bend and magnify light from distant exoplanets, effectively creating a natural cosmic telescope. Instead of needing an absurdly large lens, we could get an ultra-clear 1000 by 1000 pixel image which is sharp enough to see continents, oceans, and even potential weather patterns. How does a gravitational lens work? Imagine this: you're holding a magnifying glass and using sunlight to burn a hole in a piece of paper. That's essentially how gravitational lensing works, but on a massive cosmic scale. Instead of a magnifying glass, we use the sun's gravity to bend and focus light from a distant exoplanet. The sun acts as a natural lens, bending light from the exoplanet around its curved space-time, while a telescope positioned at the perfect vantage point captures the magnified light. This bending effect forms what's known as an Einstein ring, a glowing halo of light that contains all the visual data needed to reconstruct a high-resolution image of the distant world. By capturing and analyzing this warped light, scientists can potentially reveal details like continents, oceans, and even weather patterns on planets hundreds of light-years away. How do we get a clear image from an Einstein ring? Here's the problem: a ring of light doesn't look like a planet. So how do we go from a glowing halo to an actual high-definition image? The trick is deconvolution. The telescope wouldn't just take one picture. It would take thousands, all at slightly different angles. Then, once the images are collected, advanced algorithms stitch them together to form a clear picture of the exoplanet, kind of like how NASA assembles satellite images of Earth. This technique means that instead of blurry blobs, we'd finally get a detailed snapshot of a world light-years away. And if an exoplanet had cities, we might even be able to see the glow of artificial lights at night, which would be direct proof of intelligent life. There's just one small problem: distance. This all sounds amazing, but there's a slight issue. To use the solar gravitational lens, we'd have to send a telescope to a point 550 astronomical units away from Earth. For perspective, 1 AU is the distance from Earth to the Sun. That means we'd need to send a spacecraft about 82 billion kilometers away, or 14 times farther than Pluto. With current propulsion technology, that's like planning a road trip where your car only goes 5 miles per hour and you're driving to another country. In short, it would take centuries. How can we get there faster? NASA scientists don't want to wait hundreds of years for a telescope to get to its destination. That's why they're looking at solar sails, giant, ultra-thin sheets that use the sun's radiation pressure to accelerate a spacecraft to much higher speeds than traditional rockets. With solar sails, we could potentially cut travel time to 25 to 35 years. Long enough for scientists to work on the mission within their careers, but still a big commitment. One telescope, one planet. One of the biggest challenges with the Solar Gravitational Lens telescope is its extreme focus on a single target. Unlike the James Webb Space Telescope, which can observe multiple exoplanets, galaxies, and cosmic phenomena, the SGL telescope is locked onto just one exoplanet for its entire mission. It's like having a telescope that only takes one picture for decades. It might be an incredible picture, but you don't get to look at anything else. Now, if we wanted to switch to a different exoplanet, the telescope would have to move an enormous distance, about the same as the entire orbit of Saturn around the Sun. This isn't just inconvenient. It's completely impractical with our current propulsion technology. The best and most realistic solution: instead of one massive telescope, we launch multiple small, cost-effective telescopes, each positioned at different locations to capture images of various exoplanets. By deploying a fleet of compact telescopes, we could study multiple worlds simultaneously, giving us a greater chance of spotting a truly Earth-like planet, or even one that shows signs of intelligent life. The future of exoplanet imaging. While this mission is still in the theoretical and research phases, scientists are optimistic about its feasibility. So far, no major technical obstacles have been identified that would make it impossible to execute. The concept of using the solar gravitational lens is supported by strong physics and existing astronomical observations. If advancements in propulsion technology, such as solar sails, continue at their current pace, we could launch such a mission within a few decades. The key challenge remains reaching the necessary distance of 550 AU in a reasonable timeframe. But engineers are already exploring new methods to accelerate spacecraft. Additionally, the ability to process the Einstein ring into a high-resolution image will require cutting-edge computational techniques and artificial intelligence. If successful, this mission could mark one of the most groundbreaking achievements in astronomy, allowing us to directly see distant Earth-like planets with enough clarity to detect oceans, continents, and even potential signs of life. The next steps involve detailed planning, securing funding, and developing the necessary technologies. But one thing is certain: we are on the brink of a new era in space exploration. Why this matters? For thousands of years, humans have gazed at the vast night sky, pondering the ultimate question: are we alone? Every civilization, from ancient astronomers to modern scientists, has sought answers beyond our own world. Now, for the first time in history, we stand on the brink of uncovering the truth. Thanks to groundbreaking advancements in space technology, we are closer than ever to capturing the first clear image of an Earth-like exoplanet, a world that may hold vast oceans, towering mountains, and even signs of life. If the Solar Gravitational Lens mission succeeds, we could witness a planet eerily similar to our own, bringing us one step closer to confirming extraterrestrial life. Just as the blue marble image of Earth in 1972 transformed our perception of our home planet, the 2060s may be remembered as the decade when we finally saw another habitable world in breathtaking detail. This isn't just about science, it's about changing our understanding of the universe and our place within it. A new era of exploration is on the horizon. And that, my fellow space nerds, is how we might one day get a crystal-clear selfie of an exoplanet. No more blurry space potatoes. If you're as excited as I am about finding alien continents, oceans, or even city lights, then don't just sit there. Smash that like button like it's a warp drive. Subscribe for more mind-blowing space content, because who knows? By the time this mission takes off, we might be live streaming from Mars. See you in the future, unless of course we get abducted first.